Hello everyone, I'm Marco I'm a principal engineer at Citus Data. I usually work on Citus and talk about charting, but today I'm going to talk about a sort of side project called PG Paxos, which is a PostgreSQL extension for doing table replication through distributed consensus. So first question is like, what is distributed consensus? And it's basically a quite classical problem in distributed systems. So you have a bunch of servers and you need all of them to agree on something. For example, one of them needs to do a certain task, or one of them needs to be the leader. And you don't want to be in a situation where some of the nodes think that this guy is the leader and some of the nodes think that that guy is the leader. Or you have replicas on of some state on different machines, and you need to agree on changes, like they all need to change the state in the same way. Now, as it turns out, people have shown this kind of mathematically. If you can have arbitrary failures in your system, it's actually not always possible to there's no algorithm that kind of guarantees consensus. It's not necessarily a problem, it's just more a mathematical result. But it means you can only basically have probabilistic algorithms for consensus. And there's basically two types of probabilistic algorithms. One kind of always terminates but may not succeed, and the other one always succeeds but may not terminate. And Paxos is the latter type. So it reaches consensus but may take forever. But usually it doesn't, and that's why it's still useful. So Paxos has a bit of a bad reputation for being very complicated, and this was partly caused by the original Paxos paper called The Part-Time Parliament by Leslie Lamport, who invented Paxos. And the abstract of the paper was, recent archaeological discoveries on the island of Paxos revealed that the parliament functioned despite the peripatetic propensity of its part-time legislators. The legislators maintained consistent copies of the parliamentary record despite their frequent forays from the chamber and the forgetfulness of their messengers. So this was a analogy kind of taken too far and turned into a whole paper, and no one really understood what he was talking about. But he did describe the algorithm using like boats and people going from island to island. The idea was there wasn't a central parliament on this group of islands, and so they had to agree by sending messengers back and forth. And those get lost sometimes because the boats might get lost in storms. But anyway, it's quite a interesting yet impossible to understand paper. So later he published another paper called Paxos Made Simple, where the entire abstract was, the Paxos algorithm, when presented in plain English, is very simple. And it is actually pretty simple. He didn't quite specify how to implement it. That's also another problem with why Paxos has a bad reputation, but the algorithm itself is actually really, really quite simple. So you can kind of see it as a function that takes a key and a value, and in a group of nodes, all the nodes have this function basically, and it returns the same value on every node, and the value is one of the inputs. So one node might call this function with like key 1 and value 10, and another might call it with key 1 and value 20. Then either they both return 10 or they both return 20, but they never return a different result. And so this is something you can use to agree on a value once. And it runs in two phases. First, there's a proposer who kind of starts the algorithm, kind of the one who calls the function, basically. And it asks nodes in the system, please prepare or please participate in my proposal. And then he needs to get the majority of nodes to promise to participate in the proposal. And it's quite important to get a majority here. And if anything goes wrong, which causes you to not get a majority, you kind of start over from the beginning. You keep doing that until you succeed. If you do get a majority to participate, your next step is ask the majority that is participating to accept a value. And then the majority has to accept that value. If you can get that done, you're done. You have consensus. You've guaranteed that Paxos will always return the same value in all the nodes. So zooming into that a bit more, how that actually works. So the question in phase 1 of Paxos, the question that the proposer asks to the other nodes is, please do not accept proposals with a lower number than I. And then the node's receiving that message, and the proposer could be one of those nodes. Then it can conveniently talk to itself, and then it only needs to talk to one other node if there's three. The acceptors getting this message can say, okay, I'll participate in your proposal. Or someone else also sent this message, but with a higher proposal number. And so this proposal number just kind of starts at 0. And if two messages have the same proposal number, you kind of look at their node IDs to decide which one is greatest. So if one of the nodes responds with, oh, actually, I already promised someone else, so I received a competing proposal with number j, well, then the proposer who started says, oh, that's a pity. Well, I'll start with j plus 1, because then my proposal will win. Or a node might say, actually, we're already a bit further. I already accepted the value, so someone already went into phase 2. And then that node sends back the value. And it might be that the proposer gets back a value. It might even get multiple values. It always picks then it picks the one with the highest proposal number. And it uses that instead of its own value. So it stops. If it gets back a value from any of the nodes, it stops using its own value and uses that value instead. Or if it doesn't, if it just gets like okays from everyone, then it uses its own value. So then in phase 2, it asks a majority of nodes to accept that value, which is either its own value or someone else's value. And then the nodes getting that message can say, okay, I accept your value. Or someone came in and started phase 1 with a higher proposal number, and that node promised not to participate in my proposal because that other proposal had a higher number. So then the proposer needs to start over all the way from the beginning and try again and again and again until this algorithm succeeds. And it could be that there's another proposal which kind of keeps preventing you from finishing. That's kind of like a sort of fundamental problem in Paxos. That's why it may never finish. But you can kind of counter that with like exponential back or random back off, basically. If you get a majority to say, okay, I accept your value, then you actually know that there is consensus. And as a final step, you typically tell everyone, hey, I've learned, we have consensus on this value. And that prevents other nodes from actually having to communicate to learn what the value is supposed to be. But this is kind of a best effort thing. If it fails, that doesn't affect the correctness of the algorithm. So why does this work? These two phases, why does this guarantee that we always get the same value in all the nodes? Well, if I get a majority of nodes to accept my value, that means that no other node, no other proposer managed to complete phase 1 since I did. Because if they did, I would get back this response and not this response. So there might be other nodes who are currently still in phase 1, but no one completed phase 1 since I did. Thus, I know that when any other kind of ongoing proposal completes phase 1, actually they will see my value, because a majority of nodes accepted my value, and per this rule, all those other proposers will get back my value, and meaning that all subsequent proposers will actually use my value instead of their own. And finally, it is guaranteed that my value has the highest proposal number. Like you kind of could get into a state where someone starts phase 2 and then one node accepts the value and then the proposer dies or something. Like Paxos is kind of tolerant to any type of failure, so that's a possible failure scenario. But it's actually guaranteed that my value now has the highest proposal number that has been accepted because I know that no one else managed to complete phase 1 with a higher proposal number. So the steps in Paxos kind of guarantee that nodes will always use my value once I get a majority to accept. And if anything goes wrong during the algorithm, you always just restart. And what's nice is that because you only need a majority to accept, you can always tolerate a minority of nodes failing. So 1 out of 3 or 2 out of 5 nodes can just arbitrarily fail. And it's also robust to like proposers failing and never coming back and leaving some state. It can recover from all those situations. So that's nice, but how is that useful? Because it actually only works once. Like once a majority of node have accepted my value, I can never change it. And so this is where kind of a sort of layer of another algorithm comes in on top of Paxos, often referred to as multi-Paxos or a Paxos state machine. And the idea with state machine or state machine replication is that it's kind of a simple way in distributed systems to kind of guarantee, like, to keep state consistent across many nodes. You start from the same initial state and then you apply the same changes everywhere. And the change is essentially immutable. Like, there's just one change that happens and then you go on to the next change. So actually you can use Paxos, even though you can't actually change anything later on with Paxos, you can actually build a log of changes to some initial state. So you can call Paxos for like you can see it as a log for like the first change and the second change and the third change, and get consensus on that sequence of changes. And once you kind of know, okay, I know there's consensus on this and on this and on this, then I know that these are the changes I can apply to my local state, because I know that everyone will apply exactly the same changes, because everyone will get the same value back from Paxos. So that's nice. So how do you actually use that? Well, at this point you can do something. This is a very simplified kind of multi-Paxos example, but if you wanted to write a value, you want to make a change to the state machine essentially. What you can do is you figure out like the current round number. Doesn't actually have to be completely accurate, but what you presume to be like the latest log item. And then you run Paxos with the change you want to make. And if we're thinking SQL databases, that change can obviously be expressed as a SQL command or DML command. And then you just try to reach consensus in that particular round for that command, basically. Now there's two, like Paxos always finishes, so there's no error conditions here. I mean, probably there's some timeouts or something, but essentially it could go on forever. But there's two possible outcomes. Either I get back my query because I've reached consensus on my query, or I get someone else's query. If I get someone else's query, I just increase the round number and try again until I manage to reach consensus on, like, manage to add it to the log in some position. Now, if you want to, like, kind of read from the state machine in such a way that you see all preceding writes, again, a very basic implementation would be, I know which round number I already applied. Maybe I applied like only the first item in the log. Now I figure out what's the maximum round number for which anyone has accepted a value, and I need to get that from the majority at least. And I know that there cannot be, if I get it from the majority, I know there is no consensus on any higher round number, because then at least one of those nodes would have accepted a value for that round number. So I can just, but to get the value in the log for a particular round, I can just run Paxos, the Paxos function. Though in this case I'm reading, so I don't really have anything to put into the value parameter. So I'd usually just use something like an empty string or like something that doesn't actually change the state. Because it is possible that maybe there wasn't consensus on anything in this round. Like maybe someone started the proposal and it got accepted, but then the proposer disappeared. So it could be that there's actually no consensus yet, and that eventually we reach consensus on the empty string. But then that has no effect, so, well, why care? And once you've like replayed your log up to the maximum round number, it gets a bit more complicated when nodes join and leave, but you've basically ensured that your log is up to date with all writes that have finished. Because at the moment you kind of call like this function, you kind of get the highest round number for which there could be consensus. So there's any other writes are still ongoing. So that's nice, and we can essentially use this to build like a SQL-based replication solution where we start with an empty table and then start applying SQL commands to it. So I did an implementation of this called PG Paxos, which is an extension. So you can just run it on Postgres. I think probably works from 9.4, maybe even 9.3, and 9.5, 9.6. And it basically implements table replication in a sort of consistent fault-tolerant manner. So you can have, let's say, 3 Postgres servers, and there's a table on each of those servers that whatever write goes into that table will be visible on all the other tables in a consistent way. And you can lose a node and instantly, well, there's no recovery even, like you can lose a node. It doesn't matter. The only problem is, and you may have noticed this just from the diagrams, there's a lot of round trips. So it doesn't come for free. So you have to actually, every read has to make some round trips to get like, okay, what's the current position in the log? Every write kind of needs to do this 2 phases. You can kind of optimize it, but at least 1 phase. So it's definitely also not an alternative to things like logical or streaming replication. It doesn't really help you scale out Postgres in kind of a very fancy way, but it is actually a very useful building block for certain use cases, especially like when you're building a kind of distributed architecture and you need to, for example, have locks, like you want one machine to do something. How would you do that in a kind of highly available manner? So it can be a very useful building block for distributed systems. It's available on GitHub. So it has the PostgreSQL license. And what's kind of interesting is that the implementation is mostly in PL/PG SQL, which I found actually works very nicely for implementing distributed algorithms. Because one of the hard things about Paxos as well is like even the Paxos made simple doesn't quite specify how to implement it, like what goes into stable storage, what happens if like there's, how do you actually manage your local state in a reliable way? When do you actually f-sync stuff to disk? If you're actually implementing it in a SQL layer, you don't have to worry about most of those things because like all your changes to local state are transactional. So the implementation is a lot like there's PL/PG SQL functions that like essentially act like remote procedure calls. So there's on the client side or on the caller side, there's kind of a DB link call, which calls a UDF on the other side. And it ends up being about 1,000 lines of PL/PG SQL in total. And it also provides you, and actually that part could work on pretty much any environment like that runs PL/PG SQL. I could even work on RDS or Heroku, or as long as there's DB link. And the other part of it is it provides you with kind of a transparent table replication where like if you do an insert on a table, it uses the planner and executor hooks in Postgres to actually put that insert into the Paxos log and make sure that all the nodes have it in their log. It is still somewhat experimental. It's been fairly rigorously tested. And what's kind of nice is the implementation very closely follows the paper because it doesn't have to worry about like f-syncing and stuff. So yeah, as I said, PL/PG SQL, it's a surprisingly suitable language for implementing Paxos and other distributed algorithms. You get the transactional semantics that you need for free, kind of easy to combine a bunch of responses into a table and figure out whether you reached the majority, for example. It's very simple to implement RPC. DB link, it's kind of a simple network API. It's not that great, but it works. And you can run it in a managed environment even. So if you create the PG Paxos extension, you get a few metadata tables. One is just the groups. You can be in different, a node can be in different Paxos groups. There's a table which keeps track of the hosts. The round table, that's kind of the main one. That's actually the log of entries, the multi-Paxos log. And there's a table which just says, okay, these and these and these tables are replicated in these groups. There's some functions, and these are kind of internal. You probably would never call these functions, but there's the actual Paxos function, as I described on earlier slides, which takes a key, which is the round number, and a change, which is a SQL query. And I mean, this automatically gets called when you actually do an insert on the table underneath the covers. And then some higher level functions. Apply log gets all, make sure it has, knows the value for each preceding item, and then executes that on its own table. So this helps you get your state up to date. Even if you've been down for like an hour, you can run, this function gets run, and then your state's up to date again. And then apply and append tries to keep adding a command, and then if someone else's command gets consensus, it just appends it to the next item. And there's no concept of a master here, and any node can actually start these, run these functions. It does work a bit better if there's only one node proposing stuff, because otherwise they start competing and the algorithm might take a while. So I'll show you a live demo in a minute, just to like go over the basic functions. You start by creating tables on all the nodes. It doesn't actually replicate the DDL, as you've now probably heard a couple of times in other presentations. So you first create a group where you kind of specify the host name of the node itself, and then say, okay, I want to replicate the data table. You can also replicate multiple tables. And then from that point onwards, PG Paxos kind of intercepts all the commands that go to that table. And then on the next node, you probably want to join an existing Paxos group. So you specify the host name of the original server and the node's own host name. And Paxos does this in a sort of interesting way where actually it logs the fact that a node joined. It puts that in the Paxos log. So it can clearly identify for things that happens after the node joins and before the node joins. Because after the node joins, the size of the group has increased, so the majority that we need is also increased. So for anything that happens after that, we need to kind of take into account the new node. So when you write to a table, like you do a sort of update command on the data table, PG Paxos comes in and then under covers calls this apply and append function for the update that you wrote. And then it tries to get consensus on this query and for some log position. And once it knows that, it can kind of execute all the preceding queries, then apply the update locally, and then it's done. And when you do a select query, I mean, this is like the actual implementation of the algorithm I described before. It first gets the maximum round for which a value has been accepted, and then applies all the preceding writes. So if there were like some inserts that happened before the select started, it would see that because for those round numbers, it would get that value back from Paxos. So essentially, these reads are consistent. In fact, this gives you a whole serializable history out of the box. So I've set up a little demo of PG Paxos to use it for a kind of fault-tolerant cron service. So I have, so this is kind of a pretty tricky problem in distributed systems. Like, you want to have a cron job, but if the node fails, the cron job is no longer running. But you also might not want to run the cron job twice. Like, you can set up two nodes that both run the cron job, but then everything happens twice. So you want exactly one node to do the cron job. So you can actually use PG Paxos to kind of decide which node actually gets to do cron job. It's kind of a distributed locking problem. Like, one node will grab the lock of like, I want to do the cron job in this minute. And so in this example, like, notice that the cron nodes and the PG Paxos nodes are actually completely separate. There's also applications where they're the same. I think actually this setup generally makes more sense than, like, let's say you had, let's say your cron nodes were really big because they have to do a really big amount of work. You don't really want to have 3 of them if you only need 2. So I've set this up on Amazon, and the PG Paxos nodes are basically T2 micronodes, which cost virtually nothing, because they also don't have to do a lot of work. And then the cron nodes just kind of connect to a load balancer, which sends the connection to a healthy PG Paxos node, and there they do a write into the logs table. So yeah, I've set this up on Amazon. 2 cron nodes, bigger M3 medium nodes, and then 3 Paxos nodes. And I also have a, hope internet still works, a load balancer which sits in front of all the Paxos nodes. So if I talk to this load balancer, it kind of sends me to a healthy Paxos node. Nope, okay. So this should be one of my Paxos nodes. I've created a table everywhere saying node 1 and node 2 and node 3 to easily distinguish which node we're actually looking at. So I made a very simple locks table. You basically have some sort of app ID and a key for like, so this is the program that wants to grab a lock. This is the number or the identifier of the lock. And then it says like who actually owns the lock. And there's a primary key on the app ID and the key. So if 2 writers, let's say the 2 cron nodes, both use the same primary key, only one of them will manage to do an insert. And that's the property we're going to use for deciding which node does lock. That's good? Yeah, that's a good point. Where is that again? Preferences. That would also work. Is this better? All right. So I have some other nodes. This is, I guess, node 2 and node 3. So they all have the logs table. There's nothing, well, right now it's just an empty table. There's nothing in it, or there should be nothing in it. So to set up a Paxos group on one of the nodes, I first do a create group. So this is the external IP address or hostname of the node itself. And then I say I want to replicate the logs table. So this is just some name that we use to identify the group. And this is the table name of the logs table. So at this point, I have a functional Paxos group all consisting of 1 node. So it gets a bit more interesting to add more nodes. So, okay, this doesn't look so nice, but can I? Yeah, so the command I just run is like join this group with the host name of the original node and the host name of this node. I already run it now, so let's run it here as well. Okay, so now I have a Paxos cluster consisting of 3 nodes, and my logs table will get replicated across these 3 nodes. So if I now here do an insert into the logs table for log 1, and then on some other node, I do an insert where node 1 should be the owner, I get, oh, duplicate key violates unique constraint. Because as soon as when I ran the insert, PG Paxos first make sure the log is up to date, and that log will contain the other insert. And even if they're like concurrent, which we'll actually see in the example I'm about to show, just one of them will win and the other will error out. So now all the nodes have they have the same logs table. And the synchronization, the replication essentially happens just before I run the command. I'm going to check like, is my, like the replication actually happens while the command is running. It puts it in everyone's log. But then when you run the command, it checks, oh, is my local state actually up to date with everything that's going on? So more practical example, I have 2 nodes set up to send a tweet. Both they have the same script, and here I'm using the load balancer. So load balancer just connects me to some random Paxos node. So now it's node 3, now it's node 1. And so the load balancer has constant health check. So if one of the nodes goes down, the load balancer will send a request to the remaining nodes. I'm going to try to grab a lock for the current minute. Like the cron job runs every minute, it kind of more or less guaranteed to start just after the minute starts. Then I would kind of calculate what's the number of minutes since 1970. Yep. Oh, is it not in the screen? Okay, sorry. Is this better? Yeah, okay. So I have the script on two machines, and what both of them will do is try to do the same insert for this minute. It doesn't actually matter so much if one of them is behind, then the other one will just, if the clock on one of them is behind, then the other one will just always win. And then this might error out, and in that case the script errors out because I'm using -e. So this is a very simple implementation. But if they survive this, so there's no primary key violation, then they get to tweet as the PG Paxos account on Twitter. So let's set that up. Cron tab jobs.text. So what time it is? It's always like the start of the minute, so you always have to wait until the end of the minute for the cron job to run. So this is my PG Paxos Twitter account. It hasn't tweeted yet, or I deleted all the test tweets. And once we reach the end of the minute, so they'll both like connect to the load balancer. They'll both pretty much at the same time, like the clocks in Amazon are very well synchronized these days. And they'll both do the same insert, and one of them will go before the other because they can't, like, I mean, let's say each of them come in log item 5, and only one can be in log item 5. The other one has to be in log item 6 or greater. So one of them will win, and the other one will error out. So that is about to happen. So let's see what happens. So the expectation is only one of them will tweet. Right, and now I have one tweet. So even though both of them are running the same cron job, one of them won, namely node ending with 66. So that's this guy. And if I look at the other guy's cron log, I see, okay, yeah, I got the error violates unique key constraint. So I did this at the exact same time, probably on different Paxos nodes. Now, of course, where it gets interesting is, and the real value of something like Paxos is what if nodes go down? So, or what if the whole availability zone goes down? Like Amazon has these availability zones, which essentially each availability zone is its own data center. So let's say I can both take down the cron node and I can take down the Paxos, or the Postgres node. So this is node 3 I should be taking down. So let's just stop Postgres on, I'm not actually sure which one is cron 2, I'm assuming this one. Yeah, I can do that too. Let's do that. Or I should probably stop it, otherwise fine. Stop. All right. So my expectation is I should still be getting tweets. I think one just went through. I actually stopped the other one. Okay. So now actually if I look at my one of my Paxos nodes and I select from the locks, I can see everything is still kind of fine, even though like one of the node has been shut down. Like you can sort of see like some notices of like, okay, it's actually not able to connect to this other node, but it's fine. I can still do inserts. Like I can, okay, this is obviously already inserted. You know, the fact that this, I'll get warnings, but the fact that this node has been down doesn't actually affect my availability. Until 2 nodes goes down, then actually all these commands will block because it can no longer reach a majority, and then Paxos takes forever. So that's the, but the probability of 3 data centers going down at the same time is hopefully not so great. This is actually the, if you want to check it out, the Paxos source code. I've tried to document it reasonably well. And it's all in PL/PG/SQL, which some people might find crazy, but I quite like PL/PG/SQL. All right. So where would you use this? I think one of the most common usages is managing cluster membership. This is something that generally has to be really consistent. If like there's different nodes have a different view of like which nodes are in the cluster and which node is the leader, you can get like into bad situations, especially with databases. Automated failover is also a form of like deciding who like gets to be the primary. A job scheduler, like keeping track of kind of distributed computation jobs that are out there, and kind of you have to have like one place where you keep track of the state. As a source for metadata that needs to be highly available, or in this example, distributed locks. There's really large systems out there using Paxos. Google has a locking service that they use internally called Chubby. Amazon has a similar locking service, also based on Paxos. Distributed databases like Spanner, which is the sort of main kind of database infrastructure that Google uses, is based on Paxos. They have some older databases, one called Google Megastore, which actually architecturally is a lot like PG Paxos. It's still used for things like Gmail. So Paxos is pretty widely deployed and battle tested, I guess. And so but it always comes down to like finding like, low throughput, like you want to isolate the part of your application that is really critical but doesn't require super high throughput. For super high throughput, Paxos is not the answer. So I get this question a lot. Why didn't you implement Raft? The short answer is, well, I knew multi-Paxos quite well. And I figured I could implement it in PL/PG/SQL reasonably quickly. So I tried that and it worked. So yeah, there could be other reasons. Like the minimal implementation of Paxos is quite simple. Like Raft is a bit more comprehensive in the way it deals with like nodes joining and leaving. But it allows you a bit more flexibility in Paxos of like if you want things to work from any node, it's a bit easier to do in Paxos. And mathematically, I quite like the algorithm. Basically, the algorithm was more or less derived from the constraints of like, basically you define consensus as a mathematical formula, and the algorithm is kind of derived from that formula. So it's mathematically quite elegant, but that's not necessarily a practical advantage. So that was my talk. Are there any questions? Yep.
Do you need to share the log among all the nodes?
Yeah, that's probably something interesting I could have showed. So the question is, do you need to share the log among all the nodes? Yeah, certainly the PG Paxos nodes, like there should be 3 or 5, or the ones that actually store the state. Let me see if I can. Oh, this one's. Well, let's start this guy up. Okay. Okay, doesn't fit the screen very nicely here, but basically this is like PG Paxos internals. You can see like the SQL commands that are being logged by the cron nodes are kind of in the log. And so basically when you run the Paxos algorithm, what it initially does is write to this table, basically, and then it may be that, and basically you write to this table, especially when you accept a value, but you might not necessarily know there is consensus yet. So this node only knows there is consensus up to here, but not up to here, for example. So yeah, like every node has this log, and as Paxos runs, like more stuff gets added, or this table gets updated. But eventually, at some point, when you run the query, it kind of just replays all the commands up to the point where it's last, which it has last applied. Let's leave that's in the group table. Yeah, okay, so it kind of keeps track of, okay, I've applied the first 10 items in the log, and the next time I check, have there been any other changes, and then it applies those. It's especially like if you need one authoritative place to keep track of the state of jobs, for example, like how many has this job been restarted, how many times, like is this job, like especially if you have like workflow kind of things where whether you can start the next job depends on whether the previous job started, and the next job cannot start until the previous job started. Now you can do all these things, anything you can do in PG Paxos, you can do on one Postgres node, to be clear, but until that Postgres node goes down. So that's the difference. It provides this extra instant availability layer. Like run the actual jobs on Postgres? Yeah, I mean, you could see it more as a building block. So you can build like a job execution system on Postgres, and then keep the state for that system in a PG Paxos table. So like I even have like I set it up here. I didn't end up using it in the demo. I wrote this extension called PG cron, which is like cron inside the database. It runs as a background worker.
That's like RDBMS jobs.
Yeah. So you can set up like I want this this function to run every minute or something, and then maybe this function keeps track of. This is actually sort of a job I wrote for expiring the locks. So at some point it kind of deletes old locks because you don't want to keep these things around forever. And internally, this thing could also do things like, well, if this job is running on all the database servers, I don't want them all to do it, so I'll grab a lock before I actually do something. But I mean, you can build arbitrarily complex distributed computing architectures on top of Postgres. And yeah, I think it seems to be more where we're going with tools like, well, PG Logical. I think PG cron and PG Paxos can both be very helpful. Citus, like these extensions, they kind of are gravitating towards Postgres being kind of a building block for distributed computing architectures. I know there's people who've built like, scalable key value stores or Kafka-like systems on top of Postgres. And it is quite amazingly suitable as a building block. Like even implementing Paxos is pretty easy on Postgres, which is pretty amazing. Yep.
How, you said it's low volume. You support low volume after inserts.
Mm-hmm.
How high the volume?
I guess, so the question is, Paxos is quite is for low volume writes. How high is the volume? It's more or less 1 over the round trip time, 1 divided by the round trip time. It's kind of the theoretical maximum, more or less. Well, okay, you could come up with some more advanced implementations. Like the problem is essentially you can only have 1 write at a time. Like if 2 nodes, if you do 2 writes concurrently, they'll be competing for the same log position. So like in the ideal case, like you can actually not have more than 1 write per round trip time. There's some optimizations that people have done where you kind of like, you do a couple of writes in advance, like so you kind of make sure that you're all kind of using a different round numbers at the same time, and you could probably get some more throughput. Also, like using a single master gets you better throughput than using multiple masters. But so in general, you think of it as like up to 1,000 per second. Any other questions? Josh.
So, any plans to implement full multi-Paxos?
Any plans to implement full multi-Paxos? Define full multi-Paxos.
So then you could actually have different subsets.
Yeah, that is a good point. So if you look at the sort of distributed databases that use Paxos, like Google, I kind of like Google Megastore as an example because it's actually quite close to the way PG Paxos works. But obviously, to make this actually scale, 1,000 writes per second is probably not good enough. So what you want to do to scale it out is shard your data, and then each shard has its own Paxos group. And then actually, you can pretty much add it up. If you have 1,000 shards, and they can each do 1,000 per second, you can do 1 million per second in theory. Probably not in practice, but in theory you could. So, but what you would need for that is the kind of administration that creates all these Paxos groups, which can get kind of complicated. It would be interesting to do. So, no concrete plans, but I would like to try. Also, it might tie into other like sharding extensions like Citus or PG shard, where you just make the shard, like every shard becomes a replicated table in its own Paxos group. That should be possible. So maybe I'll experiment with that. Any other questions? I think not. Okay, well, thank you very much.